Okay, folks, this is going to be the fourth video in section 2.3 on limit laws, and sort of piggybacking off the concepts that we were doing in the previous video regarding what happens when we try direct substitution. We get a 0 in the bottom of the function, means that the function is undefined. And so if a function is undefined, there's two things that might be happening there. There might be a hole, meaning that a hole at an undefined point, let's say a function is undefined at a. So you might have something like that, though, right, where you just have the hole. And in that case, the limit is still going to exist, though, if these two sides match up like that, right? Because if they're going to the same spot, then you've got the limit at that height, even though the function value f of a itself doesn't exist. So that's okay. So we might have a hole. And there's another case where we might get what we call a vertical asymptote. So another way is, let's say the function is not defined at a, but maybe something like this is happening, right? And so the asymptote we typically draw with a dotted line is not really a part of the function. It's not really a part of the graph, I should say, but it signals what the graph is sort of doing near that point. Okay, so let's say this function could be undefined at this value a. And there's no hole, though, right? Based on this picture, it looks like what we call a vertical asymptote. And then in this scenario, there's sort of two things that could happen, though. At that asymptote, even though the function doesn't exist, the limit might exist. In this case, I would say the limit as x approaches a is infinity, because both functions are going up towards positive infinity. So there's that case. And there's another scenario, though, where we might have a asymptote, and each side is going towards maybe positive infinity, but then down here from the right, we're going down towards negative infinity. And in this case, remember, the overall limit would not exist because the two destinations are different from either side. Okay, and that's what these functions f and g were. So this picture kind of just gave some examples of that. But let me show numerically now what's going on. So let's say I'm concerned with this, the limit as x approaches 0 for f of x, and then I'm also concerned with the limit as x approaches 0 for g of x. Okay, so as emphasized in the previous videos, always try direct substitution. Even if it is going to yield a value or an expression that doesn't really exist, it's still helpful, though. It still leads us on the right track. So let's try direct substitution. Okay, so I could do that with limit notation, but if I want to know the limit as x approaches 0 of f of x, direct substitution really means just evaluate f of 0, right? Try evaluating it, write it out. It might not mean anything. So here I'm going to get 1 over x is 0, 1 over 0, right? Let me emphasize that does not exist, right? So the function doesn't exist at 0, and that doesn't answer my limit question now. So at this point, this limit is still an unknown. Whether or not it exists, still unknown, right? However, I got a non-zero over 0, and that's important. Let's see what's happening over here. Let's do the second one real quick. So let's try ds again, try direct substitution. And I emphasize for you to try direct substitution. You can do this in your head, right? We can do both of them in their head. So when I say try direct substitution, doesn't mean you have to write it out. You can figure this out in your head, but you're going to get 1 over 0, right? 1 over 0. Same thing is going to happen here. G of 0 is 1 over 0 squared, is still just 1 over 0. And again, just to emphasize, as a function value, does not exist. So this expression does not exist. 1 over 0 doesn't mean anything. 1 over 0 doesn't mean anything. So for both of these functions, f and g, if we're just trying direct substitution, we got the exact same result, a non-zero number over 0, which means the function doesn't exist. So neither function exists when x equals 0. That doesn't really answer the question, though, as far as the limits exist. However, when you get non-zero over 0, both of these functions are going to have sort of a similar behavior near 0, in the sense that both functions are going to have vertical asymptotes in the vertical line x equals 0. Okay, so non-zero over 0, if you get that over, if you get that as a result of trying direct substitution, that indicates that you've got a vertical asymptote in the line x equals whatever value that was. So in this case, x equals 0. Okay, and we've looked at both of these examples before. All right, so I'm going to emphasize this. So non-zero over 0 means vertical asymptote. In the previous video, we looked at 0 over 0 right? And we said that might be a hole, and in the first example we looked at, there was a hole. I want to discuss, to those other options. So there's different stuff that can happen, but if you get non-zero over zero, vertical asymptote. Cool. Then how do you decide if the limit exists or not? Once you reason out that you've got a vertical asymptote, then you've got to consider what's happening from the left and from the right. Okay, so we've done this example, but from the right, this guy's going up towards positive infinity, 1 over x. From the left, as you divide by negative x values, when you divide by smaller and smaller x values, meaning approaching 0, they're getting smaller, the output becomes larger and larger, except this ratio is negative, right? And so we get large negative numbers going down towards negative infinity. So this limit does not exist. And as you well know, I don't like the equal sign because this is just the sentence. This just says the limit as x approaches 0 of our function f does not exist, right? This one, on the other hand, does exist, right? Because as we approach from the right, we go up towards infinity. As you approach from the left and approach 0 from using small negative numbers, as soon as we square those negative numbers, though, we get even smaller positive numbers, right? So the ratio is positive, function's going up. So this limit does exist and is equal to positive infinity. Okay, so non-zero over 0 was our result of direct substitution, and both of these functions have vertical asymptotes, right? This one is approaching it sort of differently from either side. This one is both going up, but they both share that line, x equals 0, as vertical asymptotes, okay? So whenever you have non-zero over 0 through direct substitution, that means you're going to have an asymptote. And let me just reiterate why that happens. If you, in this case, non-zero, 1 over 0, but anything else over 0, is we can't divide by 0, right? That's not allowed. That's why the function itself doesn't exist there, right? There's no point there because we can't do that. So the function does not exist there. However, remember, always when we take the limit as x approaches 0, that means we're using direct substitution to kind of see what's happening. But the actual limit process, if you were filling out a function table or plugging in different values, as you approach 0, essentially what that means is you have a non-zero quantity being divided by something that's really, really, really small, right? That's the idea of approaching 0, is it's really small, and if you divide by something really small, the output becomes really big. And really big we think of as infinity. However, those outputs could be negative and big and go down towards negative infinity. Either way, though, that results in what we call an asymptote, okay? So for, let me just see what's going on here. Rational functions, we're investigating the limits of rational functions, meaning I've got some x's in my denominators down here, at undefined points, right? Points where you get a 0 in the denominator. And we're looking at different cases. So these examples just showed us the case of non-zero. So let's write this case, or I'm kind of freelancing right here, upon trying direct substitution, right? So you plug, in other words, you're trying to take a limit as x approaches some value. Plug that value in, see what happens. Upon trying that, case 1, let's say, and I'm randomly using the blue marker here, but it looks like it, let me switch back to black just because it's a little bit more visual. Case 1 is non-zero over 0, and that always means vertical asymptote. It means the graph is going to get really, really steep. It's not going to cross that spot. It might appear on the other side, but it's going to be kind of separated right there by that dotted line, going either up or down. And so the limit we have to investigate from both sides, right? But we've got an asymptote. Case 2 sort of has 2 outcomes. And again, I'm only looking for undefined points. So I'm going to erase this, but this thing is not a case. In other words, 0 over non-zero. That's not case 2. This is a hypothetical case, but if you get that means that's equals 0, right? Because that means you have 0 over some non-zero number, and 0 over anything else. Let's say 0 over 5. I like to say 4, because you can describe that in terms of as a fraction quarters, or you could think of actual quarters, right? Coins, so a physical object. So if you've got 0 quarters in your hand, how much money do you have? Nothing, right? You have $0, but that's acceptable. So this is not undefined, though. So this sort of case of 0 over non-zero, yeah, you could get that through direct substitution, but if you do, then the limit just equals 0. essentially that means you found an x-intercept, right? The function value is 0, so you found an x-intercept. So that's not really undefined, and so not really meant as one of these cases, although it's worth mentioning right there, which I just did. For undefined points for rational functions, if they're only undefined when the bottom is 0, regardless of what's going on the up top. So non-zero over 0 was case 1. Case 2 is if we get 0 over 0. Okay? Two results here. Might be a hole, maybe a hole, or may be a hole if you want to separate those. There might be a hole, or there still could be, maybe, might be, a vertical asymptote. Okay? And I see I have a lamp over there, so if you see this glare, unavoidable, but this just says might be a vertical asymptote, meaning that if you get 0 over 0, it's a lot of the examples will do feature a hole there. So sometimes students get too comfortable and assume it's always going to be a hole. There might still be a vertical asymptote. Okay, so maybe a hole. This is video 4. That was video 3. So 2.3 part 3. Look through that example. Okay, in that example, we plugged in, I think x went to 2 or -2, one of those values. Whatever it was, we were getting a 0 in the denominator. And originally we had 0 over 0. But what we were able to do is cancel some terms out using our replacement theorem. We canceled out a common term, and after we did that, then we got to this. Then we just got to a straight up number. We eliminated the 0 in the denominator whatsoever, and so we were just able to do direct substitution. Okay, so when that happens, you have a hole. And again, I mentioned if you graph those two from the previous video, when you replace the original function that has the undefined spot with your simplified version, the graph should look the same, except now without having an open circle, it'll just pass right through that. So we've seen this spot, 0 over 0, resulting in a hole. Happens sometimes, but let's show where you get 0 over 0. That always means you can do a cancellation. That means there's going to be common factors, common terms that we can cancel. And once we cancel those, then we have to see what happens. If you cancel those and then you run into this scenario, then it's possible that you still have a vertical asymptote, okay? Even though you had this. So let's look at an example of that. Let's say I've got this, call it g of x, is so, in the previous example we had x squared minus 4. All right, so let's say I've got that, and let's say I've got this, x squared minus 4x plus 4. Okay, so I've got this g function. Now I have a quadratic up top, so there's two values that make this thing equal 0 up top. And then there's a quadratic down here. So there's up to 2 values that make that one equal to 0. And in this case, we'll see what values make that 0. So what I'm concerned with here is the limit as x approaches 2 of this function g of x. Okay, so as our typical step 1, what should we always attempt? Direct substitution. Let me show you why we always attempt direct substitution. 2, I'll give you a preview, is going to be the point where we're going to get 0 over 0. So that's going to give us our funny business. Let's say I wanted to just evaluate the limit as x approaches 0, right? So kind of a little sidebar right now. But sometimes students are so tempted to jump in with limit techniques, they forget, just see what's going on. If I let x go to 0 here, I'm going to get 0 minus 4, right? So I'm doing direct substitution. 0 minus 4. Here I'm going to get 0 minus 0 plus 4, right? Letting x be 0 is the easiest thing because any term with an x just goes to 0. And so here I have negative 4 over positive 4, which reduces to negative 1. We're done, right? So I did the limit, I let it go to 0, and there was nothing special to do other than the direct substitution. So it's worth a try because there could be problems like that are kind of, they're trick questions in the sense that they're just so easy, you just do it like that. Okay, so we always want to try direct substitution. Let's say, though, the interesting point to discuss here is if x is approaching 2. Okay, so we'll still try direct substitution, so I'll leave that ds up there. And if I do that, up top I'm going to get 2 squared is 4 minus 4. And in the bottom I'm going to get 2 squared is 4 minus 4 times 2. It's going to give me 8. And then I'm adding back another 4, though. And so that's going to give me 0 over 0. Okay? The fact that x equaling 2 makes both of the top and the bottom 0, that means something. That means that this factor, this term, x minus 2, must be a factor of both of these quadratics. Okay? Why must that be true? And that's helpful, actually, because once you, let's say you're looking at these, this guy's kind of easy to factor, this one is kind of easy to factor, but let's say you're not that keen on factoring quadratics, and you're looking at this thing, and you're like, how am I going to do that? You know, there's a 4 there. Is it like a 4 and a 1 or a 2 and a 2? How am I getting to that thing? Well, if plugging 2 in, let's just focus on the bottom. If plugging 2 into the bottom equals 0, the only way that can happen is if this term happens to be one of the factors of the bottom. Because then, by plugging x as 2, 2 minus 2 is 0. That's what's making the bottom 0. Right? If that never happens, if you've got if you factor the bottom into 2 terms, let's say x plus something, x minus something, and you don't have an x minus 2 here though, right? You have x minus 3 and x plus 1, then 2 doesn't make either of these factors 0, right? And if it doesn't make those 0, it would not make the overall quadratic 0. So the only way that that quadratic can become 0, or that polynomial can become 0, is if it has that as a factor. So that's helpful to realize. Because it can help us factor. And so what we can do now is try to use our replacement theorem. We'll try to, since I know that that's going to be a factor at the top and the bottom, I will factor those quadratics, cancel that, and then see what's happening after that. Okay? So let me erase the direct substitution. So that was kind of like a trial step, right? So I did that. If I were doing it on paper, I'd probably, rather than erase and get little rubber shavings all over my carpet, I would leave it there as a preliminary step, an investigation, right? Showed us 0 over 0, which tells me to factor that. So now let me factor, and I'm going to do that in the context of the limit, though. So similar to previous videos, I'm re-going. Even though I did direct substitution, I'm basically starting from scratch again. So I haven't done it yet, so I have to keep the limit notation. So let me first off replace g with what it looks like. So the limit as x approaches g is equal to, I'll save some space. What I'm really looking for is this. The limit as x approaches to of x squared minus 4 over x squared minus 4x plus 4. Okay, what I'm going to do next is factor the top and factor the bottom. And while I'm doing that, I'm not evaluating the limit yet, right? I'm still going to evaluate the limit, but I'm just going to focus on what's happening inside of there, which means I still need to write this. The limit as x approaches to of, what's my new function going to be? So this is what we call difference of perfect squares. So he factors easily into what we call conjugates, x plus 2 and x minus 2, okay? And this thing, if you're familiar with the process of completing the square, or you've just taken things like this and squared them out, foiled them out, right? No, remember, we don't distribute the 2 into that, right? That means x minus 2, x minus 2. And then now you FOIL these things together. Now you distribute, and you'll get x squared. You'll get a minus 2x and another minus 2x if you're outside and inside functions, or outside and inside products, which create this minus 4x. And then finally, minus 2 times minus 2 is the plus 4. Okay, so that's the factorization of the bottom right there. So let's write that. Okay, and we see what's going on here, right? Now we see common term, which we already knew. That's why doing the direct substitution is helpful, again, because when you see 0 over 0, that told me, that happened when x was 2, that told me that this and that term have to appear, okay? But notice I've got 2 copies of that term. So that's going to come into play in a later step. So what's going to happen here, let me sort of use a color here. I'm going to write equals. I'm going to use my replacement theorem right there. So let me indicate above this equal. An equal sign is really linking 2 quantities. I'm saying this limit is going to be equal or the same as the next limit I write. Why is this limit going to be the same as that limit? Because of what the replacement theorem tells us. That's why I'm indicating on the equal sign the little RT right there. So, and I'll use the blue again. I'm crossing out those 2 terms right there. And so what I'm left with now is the limit as x approaches 2 of what's left behind, right? Which is just simply this x plus 2 over x minus 2, okay? That was our replacement theorem. I substituted that expression with this expression, okay? And if you did not watch the previous videos, if you're watching these out of order, I mentioned the replacement theorem is not noted in, it's not called that in the book, but it is in the book. I think it was page 98 in a box. And if you've taken calculus before and your professors did not ask you to do this, that's not surprising. So this is kind of my little style of asking students to represent that. Again, just so we know step by step what we're doing there. We really did. We're leaving this complicated guy behind, and now we're looking at this. Okay. So at this point, and again, I mentioned in the previous video, after replacement theorem, that means we sort of just crossed out what we perceive to be a problem. Now let's see if we've solved the problem. Let's try direct substitution again. So usually, if not always, direct substitution will be the next step after doing your replacement theorem. And that means just plug in 2 again, right? So now plug in 2. So that means whenever you do direct substitution, stop writing limit, because I'm doing it now. So I don't need to say that I'm going to do it. I'm doing it. I'm letting x go to 2. So we're going to get 2 plus an additional 2, right, as is written there, and then letting x go to 2, and then minus this 2. Okay, so we've cleaned it up a little bit. We've made progress. However, what's going to happen here? 2 plus 2 is 4, right? That seems okay, but then 2 minus 2 gives us 0 on the bottom, all right? Which means we've got non-zero over 0. What does that mean? That was case 1, right? That means we've got this function actually does have a vertical asymptote when x equals 2, doesn't have a hole. And again, a hole means the functions are kind of going to a real number, and there's just a little gap in there. That's not what's going to happen with this function. This function will actually have a vertical asymptote because of this. Because as x gets close to 2, the numerator is getting close to 4. Right? It only equals 4 when we actually let x exactly equal 2. But as we get close to 2, the top is getting close to 4. However, the bottom is getting really, really close to 0. And as we argued, close to 0 means really, really small. And then something relatively fixed, relatively close to 4, divided by something really, really small, creates function values that are really, really huge, which means we've got an asymptote. Now, finally, does that mean that this limit exists? Now you have to think about the left and the right-hand sides, right? So again, we've got an asymptote. Maybe they're both going up. Maybe one's going up. Maybe one's going down. So sort of still some investigation to do. However, now we know we've got an asymptote. Okay. So yeah, so that can happen. Let me stop there. I think that's long enough.